Dear participants of the conference dedicated to the 6th-decade anniversary of Institute of Mathematics and Computer Sciences of Republic of Moldova, we present a report called Using the Ellipsoid Method to Find Parameters of Lasso and Ridge Regression. The authors of the report are Stetsyuk and Khomiak. We represent VM Glushkov Institute of Cybernetics, Kyiv, Ukraine. In our report, we present optimization problems for finding parameters of linear regression with regularization. Linear regression and regularization will be considered according to the least moduli criterion powered to P and Q, where P and Q lie in range from 1 to 2. We will see the reason for this later. Partial cases are lasso regression, ridge regression, least squares, and least moduli. The point of our work is development of an algorithm for solving the above problem, which is developed on the basis of the well-known ellipsoid method. The keywords used are lasso regression, ridge regression, least squares, least moduli, and ellipsoid method. The ellipsoid method is central and is the basis of this method, so we will pay more attention to it. Our report consists of 3 parts. The first part is related to some facts from the history of the ellipsoid method. The second part is dedicated to the Emscher algorithm and its implementation via octave language. We will explain why the method is called that way in our report. The third part is the central part and presents the use of the Emscher program for lasso and ridge regressions, although in fact it will be a broader class of regression problems that includes the above regressions. Let's move on to the first part of our talk. It includes some facts from the history of the ellipsoid method, which we will present on the next 7 slides. These are slides with numbers starting from 5 to 11. Let's go to the first slide of the first part of the report. The ellipsoid method was proposed by David Yudin and Arkady Nemirovsky in 1976. They did this in the paper Information Complexity and Efficient Methods for Solving Extremal Convex Problems. This article was published in Journal Economics and Mathematical Methods, Issue 2, 1976. The ellipsoid method was built by Yudin and Nemirovsky based on the successive cuts method. A few months later, in 1977, the ellipsoid method was proposed by Nomshor as a variant of a method with space dilation in direction of a subgradient. This was done in an article that was published in the first issue of the journal Cybernetics. All 3 authors of the ellipsoid method were familiar with each other and maintained close scientific ties. The second slide is devoted to the Ukrainian river Dnipro, which united 2 authors of the ellipsoid method, David Yudin and Nomshor. David Borisovich Yudin was born in 1919 in the city of Yekaterinoslav, now the city of Dnipro, and in 1941 he graduated from Dnipropetrovsk University. Nom Zusilevich Shor was born almost 20 years later in the city of Kyiv, which is located on the Dnipro River. He graduated from Kyiv University in 1958. David Borisovich and Nom Zusilevich were linked by scientific interests, so they met many times further. On the third slide you see the third author of the ellipsoid method. Although he is sitting with his back to us, this is Arkady Nemirovsky. This is a photo from October 1990, when Nomshor, Arkady Nemirovsky and Yuri Nestorov were in France at one of the conferences. The caption to this photo is rather interesting: Shor, Nemirovsky and Nestorov at the ellipsoidal table. Much attention was paid to the ellipsoid method at the 11th International Symposium on Mathematical Programming held in Bonn in 1982. Here 2 scientific groups were awarded the Fockerson Prize. The first group includes Martin Gretschel, Laszlo Lovas, and Alexander Schreiber for their work in 1981, in which they proposed a number of polynomial algorithms for combinatorial problems, based on the ellipsoid method. The second Fockerson Prize was awarded to Leonid Kashyan, David Yudin, and Arkady Nemirovsky for their work in 1979, in which Kashyan constructed the first polynomial algorithm for the linear programming problem with rational coefficients based on the ellipsoid method, and the 1976 work, in which Yudin and Nemirovsky proposed the ellipsoid method. We have already seen the reference to this work on the first slide. At this symposium, Nomshor gave a plenary talk on generalized gradient methods for non-differentiable optimization using space dilation operations. This report is published in the collection of selected papers of this symposium, the title page of which will be given below. Nam Zuzulevich was proud of this work. This was an overview of the space dilation techniques that had been developed at Institute of Cybernetics since 1969. This article is a little more than 20 pages long and is still relevant. The fifth slide shows a photo of Nam Zuzulevich in Bonn, where he listens to one of the plenary lectures in the company of colleagues on mathematical programming methods. On the right side of the slide we see the title page of those selected works that were published as a result of the symposium. For the first time in Romanian language, the ellipsoid method was presented in the book Operations Research, the authors of which are Andrei Fedorovich Khometsky and Mitro Ilyich Solomon. One of the chapters of this book includes a description of the ellipsoid method according to the scheme that was adopted in the Kiev School of Optimization under the leadership of Nam Zuzulevich Shor. Note that Mitro Ilyich defended his candidates and doctoral theses under the supervision of Nam Zuzulevich. The last seventh slide is humorous, but it contains some truth, because there is a very strong similarity between space dilation and the special theory of relativity. Here, Albert Einstein recommends Nam Shor to denote his space dilation operator with the symbol R alpha at C. The R symbol written by Einstein's hand in the first photo is very similar to the R symbol in space dilation operator. In the second photo, Nam Zuzulevich is giving a speech at a seminar at the Institute of Cybernetics, which took place in the 80s of the last century. Here on the board, there is a value -1 divided by 2n squared, which we will see more than once on further slides in the course of getting to know the ellipsoid method. Now we finish the story about the history of the ellipsoid method and move on to the method itself, which is presented in the second part of our report. This part is called the Emscher algorithm and its implementation in the octave language, which we will present in the next 7 slides. These will be slides with numbers from 13 to 19. Here, the name of the Emscher algorithm is made in honor of Nam Zuzulevich Shor, where M is the first 2 letters of the name ellipsoid method. The idea of the ellipsoid method will be explained with help of a simple geometric picture. It is related to the description of an ellipsoid of minimum volume built around a hemisphere in n-dimensional space, in which the point we are looking for is localized. We will denote this ellipsoid by the symbol En, and the sphere of radius R itself by the symbol Sn. The ellipsoid En has a flattened shape in the direction of the short semiaxis A, the length of which is equal to n divided by n plus 1 per r and is smaller than the radius of the sphere, the length of the major semiaxis. There are n-1 in total is greater than the radius of the sphere and is equal to n divided by the root of n squared minus 1 per r. Transition to the center of the ellipsoid is implemented using value h, which is equal to 1 divided by n plus 1 by a. To transform the ellipsoid En into a new sphere of radius b, it must be dilated in the direction of a short semiaxis with coefficient alpha equals b divided by a, which is equal to square root of n plus 1 divided by n minus 1. Central ratio, which is the basis of the ellipsoid method, is the ratio of the ellipsoid En volume to the sphere Sn volume. This relationship is expressed by the formula given on the slide and is limited above by value of exponent at -1 divided by 2n. This value determines denominator of a geometric progression for the convergence rate of the ellipsoid method by volume, i.e., at each iteration of the ellipsoid method, volume of the ellipsoid that localizes a sought point decreases by value of exponent from -1 divided by 2n. Note that all parameters of the ellipsoid method are determined only by the dimensionality of space. This is a good property of this method, since its convergence rate depends only on the dimensionality of space. It was this that made it possible to build polynomial algorithms for both Cashin and Gretschel, Lovász and Schrijver. To transform an ellipsoid into a sphere, we need to dilate a variable space, which is done using the space dilation operator, which has the form shown on this slide. Here, alpha is the coefficient of space dilation in normalized direction in n-dimensional space, and n is a unit n times n matrix. If we explain space dilation, not on the example of an ellipsoid of a minimum volume, but in general, then for 3-dimensional space such an example is given on this slide. In 3-dimensional space we have a sphere of a radius r and direction c. If we dilate space in direction of c, we will get an ellipsoid, whose semiaxis in direction c will have the length alpha r, and the other two semi-axes in directions orthogonal to x will be equal to the radius r. Algorithms for solving a number of problems are built on the basis of this simple geometric idea. We will consider the Emscher algorithm, which is related to convex optimization problem, namely, for a convex function f at x, we need to find such a point x epsilon star, for which f at x epsilon star minus f star is less or equal to epsilon, where epsilon is a small number greater than 0, and f star is a minimum value of the function. This stopping criterion for a convex function, it can be both smooth and non-smooth, is associated with a monotonic decrease in volume. The input parameters of the Emscher algorithm are the starting point x0, r0 is the radius of a sphere that localizes the minimum point, and epsilon is the parameter with which we stop our algorithm so as to guarantee finding the desired point by the value of the function. Further, we will use the same notation g at xk for a subgradient of a function f at x at the point xk. This slide shows the B-form of the Emscher algorithm as presented by Noam Zuzulevich. The first step of this procedure is the epsilon stop criterion, which guarantees finding the desired point we talked about. In the second step, the transition to the center of the ellipsoid of minimum volume in the direction of the short semi-axis is calculated, which is determined by the subgradient of the function at the point xk. The third step is to move to a new sphere, recalculate the B matrix inverted to the space transformation matrix, and recalculate the corresponding radius of the new sphere to locate the minimum point. This slide shows code of the Emscher function in octave programming language. The program includes 16 lines of code. Each line may contain more than one operator. This is a MATLAB-like language. I think it should not create any problems for anyone who wants to program this method. On the next slides we present input and output parameters of the function. And that 16-line program code, which implements the Emscher algorithm. Let's move on to the third part of our report. This is the central part that was prepared for publication in the conference proceedings. Here we consider the application of the ellipsoid method to convex programming problem, partial cases of which are lasso and ridge regression. The results will also be presented on the next 7 slides with numbers from 21 to 27. Let's go to the first slide of the third part. This slide shows formulation of the optimization problem, the essence of which is as follows. Let the n times m matrix A, vector y of dimension m, and 3 scalar parameters be given. Lambda is greater than 0, and p and q are scalars that are in range from 1 to 2 inclusive. The central problem that we will consider is the convex optimization problem, or more precisely, the problem of minimizing a convex function f at x, the formula of which is given under number 1. This function is the sum of irrelevancies of the components of the vector y minus the sum of j from 1 to n I xj. This is the predicted value of the vector y powered to p plus lambda to the sum of moduli of the components of the vector x powered to q, where x is a vector of unknowns parameters. The second part of the function f at x is responsible for the regularization. The first part is responsible for a good approximation of y vector by means of linear regression with matrix A and vector y. The function f at x is convex. It is smooth if p is greater than 1 and q is greater than 1, and non-smooth if p is equal to 1 or q is equal to 1. It is easier with smooth functions. For them there are more methods for solving, but for non-smooth ones, fewer methods. The method we use will cover the entire class of convex functions, both smooth and non-smooth. This slide shows partial cases of problem 1. The first partial case is lasso regression, which we have already talked about a lot. If p is equal to 2 and q is equal to 1, then our function turns into the function behind the lasso method. Here it is denoted as the function f1. It is a sum of squares of deviations of components of the vector y from the predicted A times x, plus lambda on sum of the moduli of xi. Such a problem is known as a linear regression problem with L1 regularization, where lambda parameter is responsible for the regularization. This function is non-smooth. The second function is ridge regression, also known as L2 regularization. It corresponds to value of parameter p and q equal to 2. In this case, we have an ordinary quadratic function that depends on the lambda parameter. Its solution can be found analytically if the matrix has a full rank in N, because by equating the gradient to 0, we get a system of linear equations that has a solution. If the matrix has an incomplete rank, then there are problems related to the non-unity of the solution. The third case is that lambda is 0. Here, one problem degenerates into two problems, which are based on two well-known methods. The first is the least squares method. It corresponds to p equal to and lambda equal to 0. The second is the least moduli method, which corresponds to p equal to 1 and lambda equal to 0. Apart from these partial cases, we can use other values of p and q from range of 1 to 2, and this covers a number of other linear regressions with other regularizations. This slide shows formula for calculating subgradient of a function f at point x dashed. It looks bulky, but it is quite transparent. Here, the signum operation is associated with determining signs of components of the corresponding vectors, which are responsible for the regression and regularization parts. The formula for calculating subgradient is implemented using matrix functions, in fact, in one line of a program code. We will use this formula number 2 in our method based on the ellipsoid method. The fourth slide of the third part shows the algorithm for solving problem 1. We have already seen this computational scheme used in the Emscher algorithm. In this case, it is the same algorithm, but adapted to the problem. The adaptation is minor and is related to step 1, where you need to calculate subgradient of the function at the point xk using the formula from the previous slide. Otherwise, this algorithm coincides with the Emscher algorithm. It can be noted that there is no calculation of the function value here, since the ellipsoid method works as a cutoff method using subgradient directions in transformed space. This scheme is interpreted in the same way as the Emscher program, that is, at the 0 step, we choose x0 and r0 such that the xbq stars in a sphere of radius are 0. We also select the epsilon at which we stop the process. We take B0 matrix as an identity matrix and set the iteration counter to 0. Steps 1 through 5 are repeated until the condition in step 2 is fulfilled. The norm of the subgradient multiplied by the radius of the sphere in transformed space is less than epsilon. Stopping under this condition means that such a value of f is found that differs from the optimal value by no more than an epsilon. Step 3 is the same as in the Emscher algorithm and means moving to center of the ellipsoid of minimum volume circumscribed around the hemisphere. Step hk is a step taken to the center of this ellipsoid. Step 4 means the correction of the space transformation matrix, which is related to the transformation of this ellipsoid into a new sphere, and rk plus 1 is the radius of the new sphere that we will get in the transformed space. By adding 1 to the iteration counter, we go to step 1 and the method will run until the condition from step 2 is true. As a result of this algorithm, we get what is formulated on the next slide in the form of a theorem. This theorem is close to the theorem we considered for the Emscher method and means that the points xk and xk plus 1 generated by the algorithm described above, and the ratio of the volumes of the ellipsoids at the step k and k plus 1 does not depend on k, but their volume ratio is equal to the value we already saw on the previous slide. It is estimated from above by the exponent from -1 divided by 2n. This is the denominator of the geometric progression, the rate of which coincides with the ellipsoid method, and, in this case, the algorithm we are talking about. The optimal point always belongs to the ellipsoid at each step of the method. Fulfilling the condition f at x epsilon star less or equal fpq star plus epsilon means that we find the point x epsilon star with such precision that we cannot reduce the minimum value of our function by more than epsilon. To illustrate how this method works, we used a dataset on compressive strength of concrete from the UC 2017 repository. This example includes 1030 dimensions with 8 numeric features and 1 target variable. The target value in this case is the compressive strength of concrete. The strength of concrete is determined not only by the ratio of water and cement, but also by the content of other ingredients, including fly ash, blast furnace slag, superplasticizer, coarse and fine aggregates. The second part of the slide presents the result of the calculation performed on a computer with an AMD Ryzen 5 4500U processor with 2.38 GHz with a 16 GB of RAM, and the Octave program version 6.20. In this example, there are 8 variables and 1030 measurements. The starting point x0 is equal to 0, the radius r0 is equal to 100, epsilon is equal to 10 to minus 20th power. The number of iterations of the method varied from 4 to 5,000 depending on the values of p and q. Problem solving time was 28 hundredths of a second. This is for 5 program runs at different values of p and q. The results of the program are shown in the table on the next slide. What can be said about the calculation results? The table has 5 columns corresponding to 5 tasks. The first line shows the selected values of p and q parameters, and the second line shows the values of lambda parameter. Rows 2 through 9 of the table contain 8 variables found with precision epsilon equal 10 to the minus 20th. Columns 2 and 3 correspond to Lasso and ridge regressions. We can see that in Lasso regression, the variable x5 tends to 0. It corresponds to plasticizer, and this, in general, is somewhat surprising, since concrete loses its strength without a plasticizer. However, this is already a matter of interpretation of the results. As for the mathematical component, we can see that ridge regression, here it corresponds to column 3 with pq to 2, gives quite homogeneous values of unknown variables. The next 2 columns 4 and 5 show the optimal values of the variables obtained using the method of least squares and least moduli, respectively. There is some difference between the parameter values here. The last column corresponds to the option, in which p and q are equal to units. The function is not smooth. We see that in this case the obtained parameters are quite close to the parameters found using Lasso regression with lambda equal to 10,000. At the bottom of the slide there are names of the indicators that correspond to variables from x1 to x8. They are cement, fly ash, blast furnace slag, water, superplasticizer, coarse aggregate, fine aggregate, and cement age. We chose the test example in such a way that the number of measurements was about 1,000, and the number of variables was small. The situation with the time of solving the problem will not change significantly if we take a problem with 15 or 20 variables. Let's move on to the conclusions. It is worth noting that the algorithm for finding the parameters of Lasso and ridge regression was developed based on the Ellipsoid method. This is the ellipsoid method performed by Nom Zuzulevich. Formulation of the problem is quite broad and includes a number of different regressions that can be interpreted at other values of p and q between 1 and 2. This slide shows 3 references that go through conference proceedings. The first reference is the Elements of Machine Learning book, where you can find information on Lasso and ridge regression. The second reference is an article from Information Technologies and their Applications Conference, at which Viktor Stovba gave a speech in Baku, Azerbaijan, in April of this year. This article considers only one regularization. The last reference is a 2023 paper titled The Ellipsoid Method and Computational Aspects. It was written in connection with the 85th anniversary of Nom Zuzulevich Shore and is devoted to a review of various options of the ellipsoid method. This slide shows names and numbers of the projects through which the research discussed in the report is carried out. This is a Volkswagen Foundation grant number 97,775, a grant of National Fund for Fundamental Research of Ukraine, and a joint grant of Taras Shevchenko National University of Kiev and the National Academy of Sciences of Ukraine. This is the end of the report. Thank you for your attention.